There we go. Let's fix that. And hello again. Hello everyone and welcome again to another stream. We are live for another review session. Let me update the titles real quick. This should be review. Physics. Okay, let's just update the titles real quick. Let's just remove that for now and update everything. Alright, so we have again with the same student from yesterday. We have Gita for review for HSCC. No, not HSCC. IBDP physics. Sorry, my mistake on that. Now, I'll just open up the files so we're ready, and I'm gonna join the lesson now as well. I haven't opened the board yet. Hold on. She's not here yet according to that, but she should be here soon. Just making sure she's that we have 1, 2, 3, 1, 2, 3, 4, 5 files today. All right, and let's also fix the board and just waiting for the lesson to actually start. So where were we? Is it just me or is the camera like... I think it's the camera. Let's fix that a bit. Okay, the camera angle's off a bit. There we go. Looks a bit better. Alright, and let's might as well go on the board. There we go. Okay. Let's fix my camera real quick.
Hello, sorry I'm late.
No worries. How are you today?
I'm good. How are you?
Good. We're doing good. Thank you. All right. So let me just get that up. All right. Okay, and okay. So you've sent over a few questions again for today, for review. I hope, right?
Yeah.
Okay. Let's. Something's weird. Is it me or is it like I'm a little bit... Hold on, let me switch over to main camera. Am I like a little bit diagonal, slanting?
I wouldn't say so. Maybe I feel like it's the screen behind us just a bit tilted, so it makes it look like the green screen. I mean.
Okay, let's go to the normal camera, see what that looks like.
I wouldn't say it's tilted.
It is tilted. It is tilted. My left shoulder is higher than my right. See?
Yeah.
All right, I'll fix that later. Don't worry about it. Okay, so let's just go onto the board. And all right, let me share the board here as well, and let's start. Okay. Okay. All right. So first, let's go on to the first problem you sent. Let's see what it is. 12, 15, 13, 14, 17. All right. Okay, so this is the one with the disc that is rolling without slipping on the inclined plane, right?
Yeah.
Okay. Okay. The moment of inertia is given, and which of the following would be correct about the linear acceleration? The first one here, this is actually, again, usually on for the first time that you encounter these kinds of problems, it's a bit difficult to answer. But there's always a link between two things that makes it easier to solve, okay? The link, let's start with the link right away. We know that alpha should be equal to the acceleration times r, okay? All right,
Yeah.
so this is, I'm just going to put here, and this is the link to solve, okay? Okay. Let's kind of go here and actually see what's happening here. First, you're given the moment of inertia. So I is equal to 1/2 mr squared. All right. And we know that the what else is given? It's rolling without slipping. Okay, rolling without slipping. From rest. So we
So
know that
there's friction.
yeah, there is friction. There's definitely some friction here. Okay. From rest, so that means our omega zero that's going to be equal to zero, right? Okay. What else do we know? I think that's it. Okay. So which of the following is correct? Now remember this. Let's go first to the linear version. Force equals ma, right? Okay. So if you're gonna convert that, this is gonna and look for the acceleration. We're gonna get a equals f over m, right? Okay. So what we're gonna do here is um we're gonna do the rotational analog for this, wherein the torque is equal to I alpha. Okay. However, we're also gonna use the other fact that the torque is equal to um what was that again? The torque should be equal to uh is there
The
anything?
centripetal force.
Yeah. No, not necessarily the centripetal force. This is hold on. Is there anything I missed here? You're given the mass and radius r. So let's put that here. R, right? Okay. Now, the idea here that will really help out is once you identify um you know that this is gonna be a disk, so we can now change that its weight is still gonna do that. That's the weight, all right? Okay.
Yeah.
And let's also draw the friction. The friction is actually right here. And then the normal contact force, let's label that F. And then the normal contact force is gonna go like that, right? Sorry, N. All right. Um, okay. Now we're gonna look at the three forces here. Now the question here is relative to the center of mass. To the center of mass. Okay. Um. Okay. Relative to the center of mass, what is causing torque? Which force is causing torque? In other words, which one is perpendicular uh, to the radius, so to speak?
The N
The end is actually okay. If you
is
think
not
it's
perpendicular.
not
It's F.
perpendicular, it's parallel to a radius, right? I'm gonna use the a red pen here to draw that radius here that we're talking about. Okay. Same thing with weight. The weight is actually also acting along a radial line like that.
Mm-hmm.
Okay. But if you look at F, it is perpendicular to a radial line like that. So in other words, the torque is due only to the friction. And we know that the torque will be equal to the friction times R. Okay? So,
Uh, and
what?
so why are we looking that it's perpendicular?
Because the idea for torque is it's gonna cause rotational acceleration. Okay?
Okay.
And it can only cause rotational acceleration if the force is perpendicular to um, that that point we're referring to. In this case, the center of mass. Okay?
Yeah.
All right. So okay, so in this case we have an equation for torque. So this is also gonna so this is we'll write that now. That's gonna be equal to the friction times R, right? But we're looking for angular acceleration only. So from here, what can we get? We get that the angular acceleration is equal to um
FR divided by I.
FR over I. The question now is what is F in terms of something else. Let's see first if we need to look for that, right? Okay, we are basically what's that FF label? What's that thing here labeled FF? Let's see what it is. It doesn't say anything what FF is. So I'm gonna assume that's frictional force. Okay. All right. So we can already guess which ones are not the answer.
mg.
The ones that involve mg. So B and D are wrong because of these, right? Okay. Now, let's take a look here now, and that's going to give us that. And if we put this in here, oh, let's go back, zoom out to that. So we have something times r over I, right? Something times r over I. Now, one last thing here. We need to know what n is, because we also know. So again, this is if you see, this is like a 3 or 4 step question, but we do know that the frictional force should be equal to some constant or coefficient of friction times n, right?
Yeah.
Okay. Now, here's the thing. You don't even need to solve this anymore. You can if you want to, but you can already see here that n is is just w times some factor theta. Whatever that trigonometric function is, that's gonna be sine, right? Or a cosine or whatever. So you can already see here that n is also going to be w would be bigger. Okay, so n would be less than w. So you can already guess, again without calculation, which one is the answer between the two.
Wait, why is n less than w?
Okay.
Isn't w split into the component of the friction force?
Yes, that's correct. So what's happening here is the w. This again, let's do a rotation here to make it easier to see. So we're gonna rotate it a bit, right? So I'm gonna make the w, no, not the w, but the f still point to the left in this case. Okay, so that's the f, and that's our n, right? From our drawings, w must be going this way.
Yeah.
Right, and therefore this is our theta here. Okay, so in that case, because we do have the theta as given, we can already see we can see here, if we calculate that vertically the n and the w component must balance out, so n must be equal to wy, right?
Yeah.
And in this case, what's wy? That's gonna be w vertical